Good afternoon. My name is Chris Elam, East Central Service Advisor for GA Larson. This particular presentation is part one regarding the Rheem inverter products, which will cover the RP17, RP20, and RA20. All the components kind of cross over the lines there. So we'll also cover the RHMB air handlers, the EcoNet smart control, as well as the RCF communicating EV coils. So that'll go for like a dual fuel situation. So let me get started here. Okay, we'll start off here with choosing a location. It is important to allow 12 inches to the side intake louvers, 24 inches to the access panels, and 60 inches vertical for the fan discharge. If space limitations exist, the following clearances will have minimal impact to capacity and are permitted. If you have single unit applications, minimum of 6 inches to louvers. Do not reduce the 60 inches on the fan discharge or the 24 inches for service clearance. If you're doing multiple units, positioned next to each other, minimum of 6 inches clearance between the units is recommended for 2-ton models and 9 inches for 3 to 5-ton models. Once again, do not reduce the 60-inch discharge clearance out the top. Notice at the bottom, these units must be installed outdoors. No ductwork can be attached or modifications made to the discharge grill. Modifications will affect performance and operation. It is important to locate the unit in a manner that will not prevent, impair, or compromise the performance of other equipment installed in proximity to the unit. Maintain all required minimum distances to gas and electric meters, especially dryer vents and exhaust and inlet openings. In the absence of national codes or manufacturer recommendations, local codes will take precedence. It is important refrigerant piping and wiring should be properly sized and kept as short as possible to avoid capacity loss and increased operating costs. It is important also to locate the unit where runoff will not create a problem with the equipment. Position the unit away from the drip edge of the roof whenever possible. The units are weatherized, but they can be affected by the following. You have water poured into the unit from the junction of roof lines without protective guttering. Large volumes of water entering the heat pump in operation can impact the fan blade, motor life, and coil damage may occur. Freezing moisture or sleeting conditions can cause the cabinet to ice over prematurely and prevent heat pump operation. Operation requiring backup heat. Also, what can happen if the top does ice over during an off cycle and it does turn on, it will shake violently and could end up breaking the fan blade and causing damage to the coil. So if you ever come across one that the customer complains it's shaking very violently and heating, chances are that the fan blade could have ice on it. It is now off balance. It is important to select the correct refrigerant lines, line set application considerations. The following are special considerations that need to be addressed when selecting a line set. Any additional charge that may be required, fitting losses and maximum equivalent length considerations, refrigerant migration during the off cycle, oil return to the compressor, capacity losses, and system oil level adjustment. This is a note, liquid lines installed on the variable speed units are typically sized with the full capacity of the system. Vapor lines are selected based on the minimum capacity for the unit. It is possible that line set combinations may seem unusual. I saw this with a 2-ton, I believe it was. And the dealer was questioning that, but in fact, that's what it called for. For an example, a RP 2060B could require a 1/2 inch liquid line, yet only require a 3/4 inch vapor line. This keeps the pressure drop in the liquid from being excessive when on high pressure compressor speed, but maintains proper oil return and vapor velocity in the vapor line when it's burning at the low speed. Line set installation. If the tubing is to be run underground, it must be run in a sealed, watertight chase. Use and care should be used when you're routing your tubing. Do not kink or twist. Use a good quality tubing bender on the vapor line to prevent kinking. Route the tubing using temporary hangers, then straighten the tubing and install the permanent hangers. Do isolate the vapor line from the building structure. If the vapor line comes in contact with walls, ceilings, or flooring, the vibration of the vapor line in the heating mode will result in noise and vibration in the structure. If you're using existing lines, recommend to blow out with dry nitrogen thoroughly. Make sure you get any kind of debris or oil that may be remaining in the existing lines. Any debris or junk can and will end up plugging the expansion pipes. Important tubing installation practices. Observe the following when installing correctly sized type L refrigerant tubing. Check the refrigerant line size chart to ensure that you have the correct vapor and liquid size. If a portion of the liquid line passes through a hot area where liquid migration can be heated to form vapor, insulating the liquid line is required. Use clean, dehydrated, sealed refrigeration grade tubing. Always keep tubing sealed until tubing is in place and connections are ready to be made. Quality bi-flow dryer is included with all 410A heat pump units and must be installed in the liquid line upon installation. When replacing an R22 system with a 410A system and the line set is not replaced, be sure to blow out the lines with dry nitrogen to remove as much of the remaining mineral oil as possible. Check for low spots where oil may be trapped and take measures to drain the oil from those areas. That is important. We did one several years ago, and the line set, it was hidden, but there was a huge trap in there, so the oil that we had come out of there was white. If tubing is cut, be sure to deburr the ends while holding the tubing in position to prevent the chips from falling back into the tubing. Burrs such as that can affect the performance dramatically, particularly on small diameter lines. That can also stuff up your TXB or your EVs. For best operation, keep the tubing as short as possible with the minimum number of elbows or bends. Locations where tubing will be exposed to mechanical damage should be avoided. If it is necessary to use such location, the copper tubing should be protected by a housing to prevent damage. The control wiring on these particular systems, they are designed to be matched with the EcoNet smart thermostat. That's going to be your EcoNet RP20, RP17, and RA20. They're specifically designed to be matched with the EcoNet enabled air handler or gas furnace with the thermostat. So you have a fully communicating indoor and outdoor system. You do have the option to do a 24-volt legacy thermostat. They do recommend that's only used in emergency situations so you can compare the EcoNet smart thermostat. EcoNet smart thermostat insulation. It should always be mounted 4 to 5 feet above the floor, on the inside wall of the living room or hallway that has good circulation from other rooms. It is essential that the mounting location be a good representative of the temperature throughout the home. Movement of the air should not be obstructed by doors, furniture, draperies. Also should not be affected by drafts, hot or cold, TVs, fireplaces, lamps, direct sun that will skew your readings. For the EcoNet communication wiring, all that is required is 4 18-gauge low voltage control wires from the EcoNet thermostat to the indoor unit and then also to the outdoor unit. The wiring length should not exceed 125 feet between communicating controls. The maximum wire length is 500 feet. Running low voltage and conduit with line voltage power is not recommended. You can and probably will have some communication issues. An EcoNet communicating heat pump system consists of these 3 components. EcoNet heat pump or AC, EcoNet air handler or EcoNet enabled furnace, and an EcoNet thermostat. It is important to note that EcoNet smart thermostat requires continuous 18-gauge thermostat wire. Do not use phone cord to connect with indoor outdoor units. This will damage the controls. You will also have poor communication. When they say continuous 18-gauge wire, they don't want junctions in between point A and B. If you have junctions, it's best to use butt connectors or the butterfly connectors. Standard wire nuts can cause communication errors. So ideally, you want a straight shot from your thermostat to your furnace, from your furnace to your outdoor unit. It only requires 4 wires. The new EcoNet thermostats will actually have 6 terminals on it. You have an R and a C. Your R is your 24-volt power. Your C is your 24-volt common. You'll also have a E1 and an E2. Those are your DC communication wires. On the thermostat, you'll also have an S1 and S2. That gives you the option to run a remote sensor as opposed to use the actual thermostat as your sensing element. As you can see here, basically you have your E1, E2, R and C, and the same corresponding codes on the indoor and the outdoor unit. These wires need to be connected to each device, indoor, outdoor, if you're using a gas furnace, the coil as well. Once all devices are connected, apply line voltage to the indoor and outdoor units. When all devices are powered, the EcoNet smart thermostat should detect indoor and outdoor units within 45 seconds. Once the system is powered and all components are communicating with each other, the airflow settings will be automatically configured in the air handler or the furnace. The way it does that, the air handler or the gas furnace, it will have a data chip and the control board. So once it starts communicating, it recognizes this is RHMV 6021 or R96B 70. So it knows exactly what operating ranges it can be in. It will also match that up with the outdoor units as well. So you may have a RP 2036 with the RHMV 6021. It will basically base the airflow only on the outdoor unit at that point. It will run it as a 3-ton system, even though your air handler in this case has the capability of 5 tons. All adjustments for the indoor airflow are made at the EcoNet Smart Thermostat. Items that can be changed are change your airflow trim. So you can, once you have your setting, you can plus or minus your airflow 10%. On-demand dehumidification, cooling and heating airflow, and electric heat airflow. The EcoNet also has a wide range of fault and history information. It will give you specific faults, exact faults, fault codes, which we'll get into on the second webinar. Because your outdoor unit, in some cases, will give you a generic fault, whereas your EcoNet will give you a specific dedicated fault. So you know exactly what the problem is. So you can find it that way, instead of hunting around for a generic fault. You can refer to the air handler or furnace installation manual for further details on setting up the equipment and the adjustment options. If you're using the EcoNet thermostat with the air handler or the gas furnace, your dip switches do not come into play at that point. At that point, all your adjustments and all your controls are controlled from the EcoNet. Power wiring, this dictates the outdoor unit. Since these units are inverter-driven systems, voltage is very important. It is important that the electrical power, that the heat pump is acceptable within a certain range. Minimum operating range is 197, maximum is 253. We do see the high 250s some places. If you're operating 249, 250, if you spike past 250 on a regular basis, you will end up with inverter faults pretty consistently. If you get down below 197, you will also have faults. They will try to protect themselves because they'll sense those voltages, try to fault out, protect itself. But if you get enough spikes in the proper way, you will damage the drive board. Proper wiring must always be ran in a tight, rain-tight conduit. Conduit must be run through the connector panel below the access cover attached to the bottom of the control box. Connect the power wiring to line voltage lugs located at the outdoor unit. You'll see on the unit here, this is a diagram, you'll have your dedicated ground, and you'll also have a place for your L1, L2. Note, do not connect the aluminum field wire to the RP20 terminal block. And we'll kind of dig into some of that as we go along too. So this is a two-part webinar series on these units. So we're going to jump into the RHMB air handlers now. This is Rheem's communicating air handler, which is designed to match these units. For installation, you have 4 options. You have vertical upflow and horizontal left. Vertical upflow is out of the box. You also have horizontal right and downflow as well. The air filters, they are not factory installed. The external filter is required. Units should be sized for a maximum of 300 feet per minute air velocity, so that would be recommended for that type of filter. Ideally, you would want to have a 4-inch or even a 5-inch media filter to reduce static pressure. Filter application and placement are critical to airflow, which may affect the heating and cooling system performance. It will also increase the static pressure. Reduced airflow can shorten the life of systems made of components, such such as motors, limits, elements, heat relays, evaporator coil, or compressor. Consequently, it is recommended that the return air duct system only have one filter location. Systems with a large return air grill or multiple filter grills can have a filter at each opening. Down here it's note important, do not double filter the return air duct system. You're going to drive your static pressure crazy. Also, do not use very high MER filters on existing duct systems unless necessary steps have been taken, which we'll get into further a little later. They're super sensitive to static pressure. If your static pressure is excessive, over 1, especially when you start going into 1.2 and even unknown, at that point, you're going to start having inverter faults. You'll also have airflow issues, additional faults as well. So airflow is very, very, very critical. Refrigerant connections, make sure you keep your coils sealed until the refrigerant connections are made. The coils are shipped with a low 5 to 10 psig pressure of dry nitrogen. Evacuate the system before charging with refrigerant. Install refrigerant tubing so it does not block service access to the front of the unit. It's very important that if you're installing it, the service guy at a later date can access it easily without having to disconnect lines. It is important that nitrogen be flowed through the refrigerant lines while it's brazing. They have many different options to do that now. You have small adapters, several of the nitrogen gauges have it built in for a purge cycle. That will keep your refrigerant system clean. These are top-notch systems. If they're improperly put in, you can guarantee yourself some serious problems within the system. It is important also to make sure when you're brazing to protect your EXP pressure transducer, your vapor thermistor, and your copper aluminum joint. And service valves will always overheat. Use a wet rag and some type of shielding. Double torch tips are not recommended. When I braze, I make sure that I, number one, use wet rags, and then also use the thermal trap of some brand. There's different brands out there, so I try to do it, double up on it, and then don't overheat the joints that you connect. After refrigerant connections are made, make sure you seal the gap around the connections with the pressure-sensitive gasket provided. If necessary, cut the gasket in 2 pieces for a better seal. Put them on there ahead of time, they're going to melt. Okay, we're going to get into some of the components here. You have your condensate drain tubing for the RHMB air handler. Consult your local codes and ordinances for specific requirements. It is important when making these drain fitting connections to the drain pan. Use a thin layer of Teflon paste, tape, and install it hand tight. Don't get in there with channel locks and lay it to it. Over tightening the fittings can split the pipe connections on the drain pan, and also be sure not to cross thread. If you do cross thread it, you ever have to take it apart, replace the drain pan at that time. Install the drain lines so they do not block this access to the front of the unit. Also make sure they don't block the access to the filter. Minimum clearance of 24 inches is required for filter, coil, and blower access. Make sure the unit is level, preferably pitched slightly forward towards the drain connection that is being used. Also, it's important do not reduce the drain size smaller than the connection provided. You will get a 3/4 inch drain option. Preferably do not reduce that down to 1/2 inch or even smaller. You'll start running the risk of backing up and clogging. All drains must be pitched downward away from the unit, a minimum of 1/8 foot to ensure proper drainage. Do not connect the condensate drain line to an open or closed sewer pit. Obviously, smells will end up backing up accordingly. Run condensate to an open drain or outdoors. The drain line should be insulated where necessary to prevent sweating and damage due to condensate forming on the outside of the surface line. A big one, the condensate trap has to be installed. If not, the bulk of your water will just flow over your drain pan and will not drain. So make provisions for disconnecting and clearing the primary drain line should become necessary. Install a 3-inch trap, primary drain line as close to the unit as possible. Make sure the top of the trap is below the connection to the drain pan to allow complete drain of the pan. Also, the auxiliary drain line should be run to a place where it will be noticeable if it becomes operational. Occupants should be warned that a problem exists if water starts to flow from the auxiliary drain pan. It's also important that you plug any unused drain connections with the provided plugs. Everything you need will be in the parts bag using a thin layer of Teflon paste, silicone, or Teflon tape to form a water seal. It is important to test your condensate drain pan and drain line after installation is complete. Pour water into the drain pan enough to fill the drain trap and line. Check to make sure the drain pan is draining completely and no leaks are found on your drain line fittings and water is draining from the termination of the primary line. The way I always did it, pour water in the pan, prime my trap. As I'm testing it, I can go back in any time during the test startup and I can actually watch water flowing freely from my drain. There's nothing more costly than a backed up drain, unfortunately. Get back into the EcoNet smart thermostat wiring. As we said before, the R and the C, the E1, E2, that's the only 4 wires you need for a fully communicating system. Must be a minimum of 18 gauge. Class 2 low voltage wire should not be run in conduit with line voltage power wiring. Must be separated from power wiring using class 1 wire proper voltage regulated. The 14 gauge wires must be installed from the thermostat to the indoor unit. From the indoor unit to the outdoor, wiring length should not exceed 125 feet between each unit, maximum 500 feet total. Low voltage connections are made by extending wires from the top of the air handler using wire nuts. So at the air handlers, you'll actually have wire nuts. On the gas furnaces, you'll actually have control board. See wiring diagrams attached to the indoor and outdoor sections to be connected. On the air handlers, you will have a multitude of wires. So make sure that you verify which wire goes to which terminal. Do not leave excess field control wiring inside the unit. I've seen guys pull it through and they'll have an extra 2 or 3 feet wrapped around in there inside the unit. Once you pull it through, pull it tight, make your connections. Make sure after installation, separation of the control wiring and power wiring has been maintained. If you get them too close, you can and probably will end up with communication errors. So if you want to, you have the option. They recommend it in emergency, but some people want to use an ES, EKB, or whatever thermostat. You can. You're kind of dumbing down the system, and you're losing a lot of the features. Efficiency-wise, you'll still be the same as far as SEER goes, but you're losing the features and what the customer's paying for. But in the event that you have to put one on, emergency or otherwise, it will operate as a single-stage non-communicating system. Actually turns the unit, whether it's an RP17 or an RP20 or an RA17. If you wire them up as legacy, normal 24 volts, they basically become three-stage units. You'll use your normal terminals, R, C, Y1, Y for cooling, B for heat pump, G for constant fan, W for electric heat. You also have an on-demand dehumidification rack. To achieve proper airflow on a cool for cooling or heat pump, the controller Y must be connected to both Y1 and Y2 of the air handler. The controller B wire must be connected to the signal heat pump in heating mode to the air handler. This will alert the EXB to go into bypass mode. So if you kind of bypass that and just wire straight out, the EXB will not go into bypass mode. Note W1, W2 may be jumpered together to energize all the electric heat. When a call for heat is received, if warmer air is desired, or into defrost. When using 24-volt controller, the serial communicating control will ignore any inputs to the data wire 1 and data wire 2. Class 2 low voltage wiring should not be running conduit with power wire because it will interfere with communication. Going to the heater kit. The accessory electric heaters are self-contained assemblies. Heaters come in kilowatts from 5 up to 30 kilowatts. They're accessories. They do not come on the air handlers. So you basically have a couple components to these heater kits. You have one, your electrical elements. 2, you have your auto resetting limits. 3, you have your electrical sequencers. 4, you have your circuit breakers. And then 5, you have your control voltage harness. The auxiliary electric heaters, the elements are resistive type heaters that operate off of 208 to 240 line voltage. The heaters are isolated from metal cabinet ground by ceramic insulators. The heaters are powered by the electric heater sequencers. The auto reset limit switches will shut off power to the heaters if the heat becomes abnormally high. Each heater has an auto reset limit that protects the heaters from over temperature due to low indoor airflow. So you can get that from dirty filter, dirty coil, start blocking off supply vents, and a number of things that will reduce the airflow out of the furnace. The limit switches will break the line voltage to the heater and shut them off until the air temperature cools and allows those switch to reset. You have your control voltage harness. The control voltage has a 4-pin plug that connects directly to the lower control board. The low voltage from the thermostat control energizes the indoor blower and the electric heat sequencers during a call for electric heat. The low voltage harness carries the low voltage signal from the control board and sends it to the electrical sequencer. The circuit breaker is the correct size to protect the heater accessory from overcurrent. This circuit breaker is in addition to the circuit breaker at the home panel. The circuit breaker has electrical leads that connect to the circuit breaker and to line voltage. So you basically have two breakers on each circuit. If you have a short in the furnace itself, chances are, in theory, this breaker here should trip first. If your breaker at the panel is tripping, chances are you may have a bad breaker in the panel or loose connection at the panel. You also have electrical sequencers. The electrical sequencers switch line voltage power to the resistance heaters. The sequencers are powered by 24 volts via the 4-pin wiring harness. When the sequencers are powered by 24 volts, they start a time delay period before they come on. That way not all your elements are kicking on at one time. Once that delay is expired, the heater's contact closed and the power is switched on to the heaters. In the reverse cycle, once you lose your call for heat, the timing will kick in again and start counting down. So each element will be shut down one at a time and not all at once. This kind of explains the electrical heat installation instructions. Most people do this before they wire it up. Turn the power off the unit, remove the screws from the panel covering, remove the panel. In the back here, you will have screws, remove the screws, securing the cover plate for the element installation. Remove that plate, discard it, retain the screws, reminding the top flange of the heater kit. Gently slide the heater kit through, place the heater kit through the opening, and secure it into the pre-drilled screw holes. Using the top screws retained earlier, attach the top flange to the heater kit to the cabinet. Here. For upflows and horizontal left, position on the breaker is correct. Off is left or down, on is right or up. For horizontal right installations, the breaker must be rotated 180 degrees to comply with the NEC code. If one or more circuit breaker is used, each will be labeled CV1, CV2, CV3. Always place CV1 at the bottom of the breaker bracket. Each additional breaker is stacked on top of the previous installed breaker. Put the breaker back into the circuit panel. Right here, the high voltage wiring is connected to the line side of the circuit breaker. It's connecting multiple breakers to a single source power. You will need a single point accessory kit, which is the RX BJ-A21 for 2 breakers and the RX BJ-A31 for 3 breakers. You'll have to attach the heater kits red and black power pigtail wires, respectively, to the orange and black leads of the terminal block. So on the right-hand side towards the back, you'll see basically 4 screws. You have the black and orange at the bottom, and you take the red black over to it, and green at the top. Red should go to orange, and black should go to black. Connect the high voltage ground wire to either the ground lug on the bulkhead of the air handler or the ground lug on the heater kit. So remove the 2 screws, securing the electrical cover over the control board. Connect the 4-pin plug of the heater kit to the matching connector on the circuit board. There's only one place for it to go on the board. Reinstall the cover using the 2 screws. Be sure not to pinch the wires with the enclosure cover. Sometimes you have to kind of stake it through a little bit. There's a little semicircle on the right-hand side that will allow you to kind of route all your wires to the right side and not get pinched down. Remove whatever knockouts on the blower panel to accommodate the circuit breakers of the heater kit. Clean the surface of the panel around the knockout area with alcohol. The surface must be clean and dry and free of grease and oil to ensure the cover bonds correctly. Peel off the release paper on the back of the circuit breaker cover. Align the breaker cover over the knockout area and firmly press the breaker cover for 30 seconds to secure. Replace the blower cover, making sure the circuit breaker cover is aligned with the knockouts on the panel. You can restore the foil, and you're good to go. Remove the cover. Okay, some of the various components we have on the air handler, which is typical. Some are normal, some are a little different than you should see them. You have your air handler control board, your 24-volt transformer. You have an ECM blower motor. These may be new to some of you. Number 4, you have what they call a EEV suction line temperature sensor. I'll show you. That is basically going to look just like this right here. So it actually goes just like this. You have what I call your little bullet sensor right here. This will actually take the place of your sensing ball. 2 ways to mount this. On some of them, you'll have your little clamp right here that will clamp right over the suction line. If that's not provided, in some of the models, they actually give you zip ties to do that. You zip tie this on the suction line. Do not use any kind of metal binding to try to bind this and tighten it onto the line. You will end up with a sensor failure call. You also have your electron expansion valve and your aluminum evaporator coil. The air handler control board is capable of operating the air handler with either the Ethernet smart thermostat or the standard 24-volt controls recommended in emergency zone. The control board operates the blower at variable speed based upon the requested inverter speed. The control board also has the ability to maintain precise superheat by controlling the stepper motor of the EXV valve. The control board receives inputs from the data line, suction transducer, suction pressure transducer, and your suction temperature sensor to manage the blower airflow and also refrigerant flow to the indoor coil. There are indicator lights that give the status of the communication, diagnostics, CFM, and your EXP commands. The control board has a tethered memory card that contains all system information needed to allow the Ethernet smart thermostat to auto-program itself to configure indoor air volume requirements. This eliminates the need to set dip switches and setting up airflow volume. That only applies to the EcoNet. If you use the EcoNet, it overrides your dip switches. If you don't use an EcoNet, you have to set the dip switches. They mentioned here that the memory card is tethered onto the unit. It is tethered. Never cut that. It's tethered for a reason. So if you replace a board, you pull it out, you let it hang to the side, replace your board, put the card back in. If you have to ever replace the card, they have specific cards direct replacements for those units. If you damage your card or you don't forget to put your card in, the system will not run. It will just shut down completely and display an error code. This is kind of a picture of the board here. So you've got your electrical heater connections here, your transformer, your SEC1, 2, has a built-in 5-amp fuse. Do not ever plug anything into this, what appears to be a phone jack. You have your low voltage connection terminals here and here. So you'll actually have 2 sets. This is your, what they call your legacy controls. This is your normal 24-volt wiring over here. Over here you have your E1, E2. You also have auxiliary, 2 auxiliary options, and you have 2 dry contact home terminals. You have your ECM motor connection, your EV valve connection. We have 2 little lights here that will tell you what your EV is doing. It's opening or closing. Green is opening, red is closing. Here's your suction line temperature sensor connection here. This is what your model data card will look like. And you kind of see here it's got a zip tie on it. That's there for a reason. You have your pressure transducer connection. You also have your airflow LED, and then you also have your alert or alarm LED. So if you're having an error code here, it's going to flash between 1 and 10 times. That will tell you what's wrong as well, but if you have the EcoNet, which is strongly advised, you have to pay no mind to that. You go to your EcoNet, it will tell you exactly what the code is, you know exactly where to look. Some of the component connections, LED, is powered by 24 volts from the transformer, has a built-in 5-amp fuse. The control board has a memory card attached via tether. Always keep that secured onto the unit. And always make sure it's inserted into the proper slot. You have your pressure transducer connection, which is made up of PRS. The circuit board outputs 5 volts DC to the transducer. The transducer will then return a voltage between 0.5 and 4.5 volts DC, depending on what the operating pressure is. So you can, in theory, look at your voltage and tell what your pressure is. The signal from the transducer is used to help calculate superheat and drive the position of the EXV to maintain exactly or approximately 6 degrees superheat. You have a suction line thermistor, which is connected to the control board via plug OST. The sensor is a negative coefficient, 10 k ohm resistor. The temperature of the suction line is measured by the controller and used to help calculate the superheat. The EXV metering device is a variable flow metering device that can maintain precise control of refrigerant flow. The valve is driven open in steps to either go to a more open or more closed position depending on the control compressor speed. Suction pressure and temperature of the suction line will guide that. The EXV is connected to the control board at the plug EXV. The ECM constant air volume motor receives information from the control board via plug E5. The optional heaters are pre-wired, powered by the 4-pin plug. Low voltage wires are connected to the control via pre-wired connections. Field connections are made to the air handler via wire nuts. The indicators on the unit, LED 1 and 2, verify if there is communication between the air handler and the EcoNet smart thermostat. If you don't have communication, you're going to know it ahead of time if you're going to have error code. These indicators will flash green and red when operation is normal. The green light indicates communication is being received from other EcoNet enabled controls on the EcoNet communication bus system. A red light indicates the communications are being transmitted to the other EcoNet enabled controls. When both LEDs are flashing, E1 and E2 wires are connected correctly and the Ethernet communications are working properly. The airflow LED will flash one time for every 100 CFM of airflow delivery when the indoor fan is operating. The LED rate is only applicable when 24 volt controls are used. You will not get that same flash when you're using Ethernet. From the EcoNet control, you can actually go in and check the status of whatever piece of equipment that you're using. So if you're using an air handler or gas furnace, you can go to the status. You can actually go in there and it will tell you what your RPM is, your CFM, and it will also give you your static pressure. That's important, very important, which we'll kind of get into later as well. The alert alarm LED 10 will flash between 0 and 10 if multiple status codes are active at the same time. The highest priority status code is displayed. The highest priority flash code will have the slowest blink rate. The flash code will repeat continuously until cleared or overridden by a higher priority code. The EXV LEDs 3 and 4 will light when the control is attempting to either move open or closed. The green LED indicates it's opening. The amber or red is that it's closing. If you power the unit up, there at that point you'll see the green, solid, and the red. Once it's basically stabilized, at that point you'll only see small flashes of green and red because it's only opening small increments. The diagnostic error codes will report a system of faults by flashing on LED 10. If the system is connected to an EcoNet, it will also be displayed specifically at the EcoNet as well. The air handler control board, red alert alarm LED will report errors that are due to potential problems with the control board, memory card, sensor data, thermistors, or transducer, or blur mode. The next table here will show us the different faults. So if you've got a 2 flash, you will not run. You have a no model data card present. A 3 motor size is not correct for the model air handler. The data card will store all that, horsepower motor, everything. So if you put an incorrect blower motor in there, it will recognize that and it will not run it. So you kind of see here that LEDs will be your 2 flash. If you actually go to the EcoNet, it'll give you a very specific code. A102, whatever, A101. So you have another one, A104, motor no run fault. You see a motor not working. You've got multiple motor codes. You've got your return air sensor out of range. Your leaving air sensor out of range. Your evaporator through-twister failure. No valid suction temp, suction pressure, and no control fault. Yeah, actually, it's almost 1 o'clock here, so let's take about a 10-minute break, and we'll come back at 1:08. Pick back up. Okay, we'll start again here after our break. Okay, another component of the air handler has a 240 volt step down transformer. The primary volt transformer is wired for 240 volts. 208 volts is supplied. The primary tap must be moved from 240 to 208. If the primary tap is not moved, the secondary voltage will be below 240 volts DC. Low voltage, erratic control is likely to occur. The ECM blower motor on these are dedicated ECMs. Consists of a 3-phase variable speed motor and a control module. The motor receives line voltage from a connection made at the primary side of the transformer. The motor control and speed commands are transmitted on the control to the motor from a 4-pin plug labeled P5 on the air handler board. The blower motor is a constant CFM ECM motor and acts to maintain a constant CFM delivery to the system. The air handler furnace manufacturer runs a series of tests at various external static pressure and CFMs to map out the performance of the motor, blower, and unit combination. A set of coefficients are pre-programmed into the memory module that tell the motor at what speed to run to deliver its constant CFM regardless of the static pressure. As the static pressure increases, the motor senses the load on the blower wheel has changed and will increase the speed of the motor to maintain the programmed CFM. The power and amperage of the motor will also increase. If the static pressure continues to rise, the motor will eventually reach its maximum rated amperage and begin reducing its speed and torque to stay below that limit. That's what they call fallback. So at that point, the CFM will begin to fall off as the static pressure continues to rise. The airflow LED will blink appropriate code for the requested air volume, not the air volume being delivered. That's key to your static pressure. So if you're going to sell, especially if you're going to sell a full communicating inverter system, do a static pressure test on the existing ductwork before you sell it. Otherwise, if you realize after the fact that your static pressure is excessively high, it's hard to sell ductwork after the fact. So kind of preempt that by checking out the system of ductwork ahead of time and then adjusting and modifying the ductwork as necessary. You have your EEV suction line temperature thermistor, which I showed you earlier. That basically becomes your sensing bulb on a normal TXV. That's what is help use to calculate the superheat and the EV position. You have your suction pressure transducer. The transducer measures the suction pressure at the indoor coil. You also have them on the outside unit as well. The transducer converts pressure to a readable DC voltage. The control board converts the voltage from the pressure transducer and then calculates a pressure. You can also, if you have the EcoNet hooked up, at any time you can actually view, it'll give you the pressure of the indoor and the outdoor based on the transducer readings. The pressure is measured on the circuit board in the calculation of the suction vapor superheat at approximately 6 degrees. The pressure transducer is powered approximately by 5 volts DC. The transducer receives power from the circuit board on the red and black of the transducer. The transducer then will return the voltage back via the green wire. The voltage returned will be anywhere from between 0.5 and 4.5 volts DC, depending upon the pressure that is sensed. And this is basically what you have a transducer. These are 3 wires. So not much to it. You also have your electronic expansion valve. So when you think about EEVs, the electronic expansion valves, they basically come in 3 components. You have your controller, which could be the RCF small board, which we'll get into. It can be the air handler control board, or in the case of the outdoor unit, it can be the variable speed control board. So you have your EEV, which is the black rubber piece here. That's your motor. You have your actual EEV valve body, which is the copper, and then you have your control. Basically, the EEV is an electronically driven refrigerant metering device. A small stepper motor is used to open and close the port. This is done in response to signals that are sent to the air handler control board. The valve adjusts refrigerant flow to the evaporator coil based upon suction pressure, suction line temperature, and the cooling demand. Factory set is approximately 6 degrees superheat. When servicing the expansion valve, be aware that there are times the EcoNet smart thermostat ignores the suction line resistor and transducer inputs when controlling the ESB. The control board is programmed to ignore short duration changes in pressure and temperature, which allows for more stable operation. Failure to understand this key operating feature of the system could cause a technician to assume their air handler control board is not responding to changes in the suction and temperature. The EXV has a valve, a body, a valve, and a motor to drive the valve open and close. The motor simply snaps onto the body. The EXV is powered by the air handler control and the EXV plug. The motor has windings that are pulsed with a 12-volt DC voltage from the air handler control board. The pulsing voltages rotate around the valve motor, which creates magnetic pulses that turn the valve open or closed. When the air handler control board sends an open or closed pulse, the corresponding LED will illuminate. If the valve is being driven open, the green light will be on. If it is being driven closed, the amber or red will be on. If the valve is being driven fully open or closed, the corresponding LED will flash rapidly. These valves have 500 steps. In the control board, you'll see an option for a 1600 EEV motor, which that's not being utilized yet and may not be for some time. So these current motors have 500 steps. If you change it to 1600 by turning the dip switch on, you're going to have some serious erratic operation. 12-volt DC signals are usually momentarily transmitted, so you can actually keep your eye on if it's on or off. And the dip switches related to the EEV, the air handler, and also the RCF coil board has 3 dip switches. The factory superheat, which you said is 6 degrees. So your first switch, they're all off from the factory. Your first switch is for your step motor. So it's in the off position for 500 steps, which is correct. You turn that on, it thinks it's a 1600 step motor. Second Two dip switches are designed to make superheat adjustments on a 24-volt control model. EcoNet systems make the adjustment via the indoor control. The factory set superheat has been determined for the best setting for all models of the air handlers, as well as the RCF coils. There are some instances where it can be slightly off calibration, where you may try to dial in a specific. So the superheat can be adjusted to either negative or -2 degrees superheat, so about 4 degrees, or you can go +4, up to +4, which will give you 10 degrees. Show you the valve parts first here. This is what you're typically going to have right here. This has been removed from the unit. So this is your actual EXB body. You have your two chat lift connections. So if you have to replace one, it's easy enough to do. You have your little O-rings in there. So this is the actual EV itself. This is your motor. From the factory, it should be just like so. It's a good idea to anytime that you come across an EV, to always make sure that you press down on it. If it's even slightly off a little bit, and I ran into this with a couple other brands before, you will still hear the clicks, you will still feel the clicks, but it can't actually control the motor. So as a good practice, always make sure you get on there. You don't have to kill it, just make sure it's down and it's secure. With the basic valve operation, upon power up, the valve will drive fully closed. Then the valve fully opens. When a call for cooling takes place, this valve is fully open or in the driven open position. After a brief time, the valve moves to a mid position and begins to move in response to the commands from the air handler. The outdoor unit is a heat pump. The control system requests for a call for heat. The valve goes to a fully open position to allow liquid to bypass the metering device. If you go into the EcoNet, it'll actually show you 496 is typical to see. You see a 496 valve position, that means it's completely open and bypassing. The control board reads suction line pressure and temperature. Should the suction line sensor read 209 psi/g or greater, the control board knows the reversing valve has shifted into heat mode. If the suction pressure sensor does not immediately sense to 209 psi/g, but the suction temperature sensor indicates temperature above 90 degrees, the EXB will drive open. When the heating or cooling cycle ends, the valve opens for 5 minutes. That's every cycle. This allows for refrigerant in the evaporator to absorb additional heat during the off cycle. After 5 minutes, the valve then fully closes. It then fully opens and is ready for another cycle, cooling or heat cycle. The EXB has a cooling mode floodback prevention cycle that protects the compressor from potential liquid floodback during run operation. If the suction vapor superheat is sensed to be below 5 degrees for more than 5 seconds, the air handler control will adjust the valve to a more closed position. The control will wait an additional 5 seconds to see if the reduced refrigerant has corrected the low superheat. If the superheat is still low, it will make another closed position move. Keep repeating the process until the superheat is back to acceptable levels. The aluminum evaporator coil with the horizontal condensate drain fan The coils are all aluminum, as you can see, except for the aluminum copper connection. It's rated for 410A refrigerant. The coil does have a holding charge of nitrogen that needs to be released when the system is installed. The evaporator coil has a built-in horizontal drain fan that is used for both horizontal left and horizontal right discharge air installations. The air handler ships with 2 additional coil mounts, coil rails that are used when the air handler is configured for a horizontal right air discharge. We'll get into the RCF coils now. If you haven't seen one of these, they look identical to the existing coils, except they have an EV, controller, transducer, and sensor on. The RCF coils come in both cased and uncased models. Case models can be installed upflow, downflow, horizontal left, and horizontal right configurations without any modifications or accessories. Uncased models can be installed upflow and downflow without any modifications. For horizontal applications, installation of a horizontal drip shield and water management parts are required. Transitioning. It's not uncommon to have a smaller furnace or a larger coil. Coils can be installed with mismatched coil cabinet widths using a transition fitting. When the coil and furnace widths are mismatched by 2 sizes, a 6-inch minimum length transition fitting is required between the coils and the furnace. If the mismatch is only 1 size, the coil should be centered on the furnace. No transition is required. Okay, let me show you here the EXB board. This was cannibalized from another unit here. So inside the unit, the RCF coils that contain the valves, this is what you're going to see. Take the door off, you'll see this hidden in here like this. Put the switch up here, you'll see your various connections. Now here are your dip switches. These are your low voltage connections here. It does seem strange to have an electronic control board that's actually inside a cold, wet, damp area, but with the doors shut and sealed, to my knowledge, I haven't seen a whole lot of them with that. They're pretty well protected. This is a little bit different than the additional wiring. So this is used if you're using a gas furnace with the inverter outdoor unit. So for proper operation, the EXB control requires 24-volt power and staged operation signals. This following diagram should be used to connect the leads provided with the cased coil to the thermostat wiring. Used with an EcoNet Smart thermostat. So basically down here you have, you'll see the connections here, your suction pressure transducer, your coil temperature sensor, your EXB motor, the 3 dip switches, and here you have R, C, Y1, Y2. Excuse me, you'll notice you don't have an E1 or E2 here. So basically you have 4 wires that will go back to your furnace control board. One will tag into your R, one will tag into your C, one will tag into the Y1 terminal of your control board, and one will tie into the Y2 of your control board. So this is looking for more 24-volt signals here than a true communication, like you see in the air handler. So if you hear the uncased coil end shields, on the side here, all uncased coils come equipped from the factory with sheet metal shields at the front and rear of the coil. The purpose of these shields is to isolate the aluminum coil tubing from copper residue left on coil insulation by the original copper, or any copper that could have been there. Copper residue or copper oxide in contact with the aluminum tubing in the presence of moisture will result in galvanic corrosion and lead to leaks in the aluminum tube at the contact point. These shields are to protect the coil from galvanic corrosion. The standard nomenclature here, the first letter is whatever brand it is. This case here, Rheem. The C is your coil. This says F. It's a furnace coil. The next one will give you your capacity. This case is 24. The next one is your width. The next one is your efficiency. So you have your choice of standard, mid, high efficiency, or ultra efficiency. The next one is your T. This is what you're going to see with a regular TXV. If you have an E, that's going to be a EEV. Your A is your major series. Your M indicates that it's a multi-position coil. And here, this is a U, so that stands for uncased. If it was a C, it would be a case. Your last one here, this is a C. It's your minor series. So if you were to open one of these coils up, this is what you see here. This is that little box that I showed you. Now, so right here, so you've got your non-communicating board. You've got your EEV right here. The 4 is your pressure transducer. It's going to your line. Right here is your suction line resistor. That's going to act as your sensing bulb. And then you also have your various drain plates. So this is a close-up of the non-communicating control board. Right here is the low voltage connections, your R, C, Y1, Y2. They're going to be hardwired right into your control board to the appropriate terminals. Here are your LEDs, because it will actually give you code as well. You have to take the coil door off, open it up to actually access your coil, your codes. Your suction pressure transducer terminals here, suction line resistor connection, and your EUV. Once again, these are your dip switches. From the factory, they are in the off position. Just to leave them in the off position. Unless you have to adjust the superheat in any fashion, you don't want to use 2 and 3. So if you were having an issue, for instance, with a dual fuel, and you had an issue on the inside, your outdoor unit may not pick it up at first. But if you were to open up the control board, take a look, you'd have a series of four flashes. Only suction line is valid, suction pressure coil not valid. No valid suction temperature. Your valve is near the open position, or your suction pressure is out of range. If faults 1, 2, or 4 occur, the EXV will move to a default position for the mode of operation. If failure is in cooling mode, the valve will approximately move to 30 or 40% open. So you'll still get some operation. When the code is operating in heating mode, the control board will flash 4 times to indicate the suction pressure temperature is out of range. And that's a normal condition. If a failure of the suction pressure or suction line temperature sensor occurs in heating, depending on the compressor speed, the EXV may bypass sufficiently not to cause abnormal system damage. However, if the system is operating at high speed, there could be high pressure error or pullback of the inverter, where your inverter starts to actually slow down. Once again, this is your EEV, same EEV. In this case here, since it's a totally non-communicating, it's looking for the inputs from the sensor, the transducer, and then also the Y1 and Y2 signal to help determine what position it should go into. This kind of goes over your dip switches again. Your switch 1 is for your motor. You put that on, the motor will now think it's a 1600 step instead of a 500 step, and you end up with some erratic operation. 2 and 3, so off and off, in this case, gives you a pre-configured superheat setting of 10. If you want to change it to 6, 8, or 12, you can by adjusting 2 or 3. So you have your section line for this temperature sensor right here. You'll see here it has I believe that's the zip tie in there. It's like this. Some of them have a little clamp that will just kind of wrap around there. Some of the newer models, they're actually shipping with the zip ties right here. So, put your 2 zip ties, got your insulator right here. That should always be mounted on a flat surface. Don't mount that, like in this case here, on the expanded part of your flare joint. Your joint there. Make sure it's on a good, solid, flat connection. The coil will ship with all the plugs that you need to plug up your unused ports. Will also come with 2 threaded 3/4 inch 45s. So it kind of makes it everything you need to take off is in the shipping bag that you receive. The sequence of operation for the RCF coil control board, you receive a signal of a Y1 or Y1 and Y2. EXB will move to a predetermined position for cooling. Then at that point, the EXB will indicate the movement of valve. Superheat will be maintained at the level set by the dip switches. When the call for cooling ends, the valve will move to the fully closed position for a period of time, 5 minutes. Once this time expires, the valve will move to the open position. So in the off cycle, if you have a heat pump, and you have a EEV coil on the inside, during the off cycle, usually for 5 minutes, both EEVs are wide open. They'll be positioned at 496 steps. The control board in heating mode, the control board will receive a Y1 and or a Y1, Y2 signal. It will move to the predetermined cooling position. The refrigerant will flow. The suction pressure and later on will get hot. The EXB check valve will bypass the high pressure refrigerant. The transducer and the suction line sensor will report this to the control board. At that point, the EXB will move to the fully open position. When the call for heat ends, the EXB will close after a period of time. Condensate drain tubing. Consult your local codes and ordinances for specific requirements. Install drain lines that do not block service accesses to the front of the unit. Minimum clearance of 24 inches is required for filter, coil, or blower, and service access. Make sure the unit is level, preferably slightly pitched, toward the primary drain connection so the water will drain completely from the pan. Once again, do not reduce the size of the drain line. Always make sure they're pitched downwards all the way through, at least 1/8 per foot, to ensure proper drainage. Again, do not connect constant drain line to a closed or open sewer pit. Once you receive your coil, in the box, you will receive field installed duct flanges if necessary. The 4 pieces, they're shipped with the units. Install the duct flanges as needed on top or bottom of the case, coil casing. See right here. And all your holes are already pre-filled for it. There is a plenum, 2 plenum adapter accessories. The RXBA-AE. This adapter accessory is used for a 24.5 wide cased coil, coil. This allows for a 24.5 inch wide cased coil to be installed on a 28-inch wide oil furnace. This is a field installed accessory only. The RXBA-AC, this plenum adapter accessories for installation on cased cooling and heat pump coils. This allows a nominal size coil to be installed on the next smaller size gas or oil furnace. This accessory is used for installation on coil casings to fit gas or oil furnaces only. This accessory is not designed to be used for electric furnaces. Okay, I'm going to stop this portion here for the RCF coils, because on the next webinar, which is tomorrow at 2 o'clock, we'll actually jump into that. We'll get into the components of the outdoor unit. A lot of these components are the same features. Then we'll go over the outdoor unit, we'll go over charging, airflow, and diagnostics. So it's kind of a lot to take in. They're actually not that difficult to put in service, especially if you use the Ethernet thermostat. It will literally give you walk you straight through to the expected fault. It's a determined fault, so you're not having to jump around and troubleshoot. It will tell you exactly what the problem is. If you're using the actual diagnostic codes, it'll still get you there. It could just take a little longer to get there. So, but if you have any questions, please feel free to call me, email me. I put my name, number, and my email off in the chat there. So please feel free if you have any questions at any time. Give me a call. I appreciate you attending the webinar today. So if I can help you in any way, please let me know. Hope you'll attend the next webinar. So it'll be tomorrow at 2 p.m. Thank you very much, and you have a good day. Thank you.